Alright, so we're continuing to talk about trig, and in this case we're going to talk about right triangle trigonometry. So everything we're going to deal with here is going to be in a right triangle. What it does is it limits us to how much we're going to look at. You're going to see later when we get into the unit circle how we take this right triangle and we develop it into the coordinate plane system. We're not going to do that just yet. We're going to just talk about triangles first. Now, we've seen that in a unit circle. Actually, we haven't seen in the unit circle. We will later. The radian measure of the central angle is equal to the measure of the intersected arc. Thus, the value of the trigonometric function of the real number t, blah, blah, blah. Anyway, based on our angle here, we have the opposite side, the adjacent side, and we always have the hypotenuse, which is always opposite the 90-degree angle. Now, from these three parts, we can come up with 6 different ratios of one side to another. Now, what this does is for any given angle, here's the neat thing, for any given angle, the ratio of the length of the side opposite to the length of the hypotenuse is going to be the same, no matter what size the triangle is. And that's true of all of these. It doesn't matter what size triangle we're dealing with, the cosine of a certain angle, whatever it may be, you know, if you have the cosine of a 45-degree angle in one triangle, the length of the side adjacent to angle theta over the length of the hypotenuse is going to be the exact same number as it is on if you've got a cosine of 45 in a triangle that is 17,000 times larger than that. The ratio is always going to be the same. And that's what all these things are. The sine, the cosine, the tangent, the cosecant, secant, and cotangent, they're nothing more than the ratio of the sides of a triangle. And they are a way to relate the way the sides relate to one another according to whatever angle we have there. Now, each of these trigonometric functions of the acute angle theta is positive. Observe that the ratio in the second column are nothing more than the reciprocals of this one. And here's a little way to remember it. The first column, if you need to. And here's the whole idea of the fact that it doesn't matter what size the triangle is. If this angle equals that angle, then this side to that side's ratio is equal to that side to this side's ratio. Same thing here as well. You can see it in both of those. I'm not going to say that again. You can read there. You can pause the video and read that if you need to. Now, let's find the value of each of the 6 trigonometric functions of theta. So we've got sine theta we're going to find. We've got cosine theta we're going to find. Actually, let me make a little more space there. Cosine theta and tangent theta. And then we're going to have cosecant theta, secant theta, and cotangent theta. Now, sine, remember, is the opposite over hypotenuse. And when you're talking about opposite over hypotenuse, remember, you're always basing opposite and adjacent over what the angle you're dealing with is. So instead of saying theta here, I'm going to go ahead and say A. And that, because that's labeled, I could do it with either one. But let's say this is not labeled right here, and I wrote theta here. Well, now 12 is the opposite and 5 is the adjacent. So it's always based on what angle you're dealing with. And here we're dealing with angle A. So sine A is opposite over hypotenuse. And if we know that A is 5 and B is 12, then what's C? Remember, we can find that by A squared plus B squared equals C squared, Pythagorean's theorem. So we've got 25, that's 5 squared, plus 144, which is 12 squared, That equals c squared. When you add these together, you get 169. And that means that c is going to equal 13. So we end up with respect to alpha here, or sorry, theta, opposite over hypotenuse is going to be 5 over 13. And the cosine adjacent over hypotenuse is going to give us 12 over 13. And tangent is opposite over adjacent, so that's 5 over 12. Now, these over here, remember, they're nothing more than the reciprocals of these. One of the things you need to remember, a lot of people get it confused and say that sine and secant are reciprocals. They're not. They want to think that because the s's start the same, so, oh, they should go together. Well, they actually don't. Same thing with cosine and secant. A lot of people want to put cosine and cosecant together, but they don't. They're not reciprocals. So cosecant being the reciprocal of sine means that this is going to be 13 over 5. This one's going to be 13 over 12. And this one's going to be 12 over 5. Now, one thing that you need to know, if we had gotten down here and this was not a perfect square, let's say this had been something like 41, I think you run into this at some point, not really sure, then c is going to be the square root of 41. So that means that your hypotenuse here, or well, those two places right there, would have been a square root, so you would have had to rationalize where you don't have a square root on the bottom. So make sure that you understand that you've got to do that in case you have a square root on the bottom. You need to rationalize it away. Alright, so let's do the same thing here. We've got sine theta, cosine theta, tangent theta, cosecant theta, secant theta, and cotangent theta. Now, based on our theta here, we got the opposites 1. We don't know what the adjacent is, and we got to find it out from the hypotenuse and Pythagorean's theorem, but the hypotenuse is 3. So we know that a squared plus b squared equals c squared. When we plug everything in and square it, we're going to end up with 1 plus b squared equals 9. So we can subtract from both sides, and b squared is going to equal 8, which means b is going to be the square root of 8, which equals 2 square roots of 2. Alright, so that's going to be my adjacent side. So the sine is opposite over adjacent, so it's going to be 1/3. The cosine is going to be adjacent over hypotenuse, which is going to be 2 square roots of 2 over 3. The tangent is opposite over adjacent, so that's going to be 1 over 2 square roots of 2. Now here's where we got to get rid of the square root on the bottom. What we're going to do is we're just going to multiply by the square root of 2 over the square root of 2. 1 times the square root of 2 gives me the square root of 2. 2 square roots of 2 times the square root of 2. Well, remember, when we multiply these two right here, we're going to end up getting 2 out of it. And out here in front, we're essentially saying 2 times 1. So we've got 2 from the coefficients. We got another 2 we're multiplying coming from the radicals, so that's going to be over 4. So that's your answer right there, square root of 2 over 4. Alright, cosecant, once again, is reciprocal of sine theta. So that's going to be 3 over 1, or just 3. The secant is reciprocal of cosine, so we end up with 3 over 2 roots of 2. Once again, we got to rationalize that denominator. So we end up with 3 square roots of 2 over 2 square roots of 2 times 2, well, we've already, or times the square root of 2, We've already done it right there, so it's 4. So it's 3 square roots of 2 over 4. And then the cotangent is the reciprocal of this, so 1 over 2 square roots of 2 flipped over just gives us 2 square roots of 2. Now notice if we had gone all the way over here and we just flipped this over, we would have gotten 4 over the square root of 2, and that means we have to rationalize again. So if you had to rationalize to get the final answer here, go back to what you started off with and you don't have to. You can just flip that thing over. Now to show you, just in case you're curious, if you get the same thing, 4 over the square root of 2, and I'm multiplying by the square root of 2 over the square root of 2, and that's going to give me 4 square roots of 2 over 2, and then what happens with the 4 and the 2? Well, these are going to simplify to get 2 square roots of 2. Remember, you cannot cancel this 2 into that radical because you can't cancel into a radical. 2 has a value of 2. The square root of 2 actually has a value of 1.41. So remember, that's not 2, that's the square root of 2, which is a different number from 2. So you can't just knock those things out and simplify. Be careful doing stuff like that, because it's not right. All right. To find the sine of 45, cosine of 45, and tangent 45, we're going to use the special right triangle. And you can use the special right triangle to find 45-degree angles, to find 30-degree angles, and to find 60-degree angles. We're going to do the 45 today. You're going to need to figure out the 60 and the 30. By the way, they both come from the exact same angle. They just flip. We'll talk a lot more about that when we get into the unit circle in the next unit. So right here with sine 45, cosine 45, and tangent 45, or pi over 4, you're going to end up with opposite over hypotenuse, 1 over the square root of 2. We got to rationalize. So we end up with the square root of 2 over 2. Cosine adjacent over hypotenuse, 1 over the square root of 2. And guys, if you're doing the exact value again, you don't have to work these out each time. Now you've got to work it out once to show me that you worked it out, but you don't have to work it out every time. And then of course the tangent of 45 is opposite over adjacent, which is going to be 1 over 1, which is, well, just 1. Now these are important to remember because those are going to be on your unit circle that we're going to start putting together in the not too distant future. But these are good ones. You need to memorize these. You need to memorize and know these. Sine of 45 and cosine of 45, tangent of 45, yeah, you can figure it out if you know these two. And 45 is nothing more than pi over 4. So know them both as sine of pi over 4 and sine of 45. All right, so let's go ahead and look. I said I was going to let you guys do it, but let's go ahead and look at it because it'll make things a little easier. We'll do the 60 degrees, so it's kind of oriented the way we're used to. Cosine 60 and tangent 60. All right, once again, we're doing this based off of the special right triangle, 30, 60, 90 triangle. So if we're dealing with 30, that's what we're doing in reference of. So opposite is the square root of 3, adjacent's 1, and hypotenuse, of course, is going to be 2 because it's opposite the 90-degree angle. So if the sine of 60 is the square root of 3 opposite over the hypotenuse 2, so it's square root of 3 over 2. The cosine of 60 is adjacent over hypotenuse, and that's just going to be 1/2. And the tangent of 60 is the square root of 3 opposite over 1 adjacent, or just the square root of 3. Now, here's the thing. What happens when we go from talking about the 60-degree angle to talking with reference to the 30-degree angle? What changes? Does the hypotenuse change? No, it stays the same. It's the exact same one that it was before. The only thing that's going to change is the opposite and the adjacent. So that means these two right here are going to swap places, or the values anyway are, and this one down here is going to flip over. So what we end up with, if we do the sine of 30, let me change colors here. Let's do my purple. If we do the sine of 30 degrees, the cosine of 30 degrees, and the tangent of 30 degrees, even if we don't know that it just flips around, flips over, adjacent and opposite swap places, we can do it the same way. Based on 30, the opposite is now 1, and the adjacent is now the square root of 3. The hypotenuse is the hypotenuse is the hypotenuse. So when we do the sine of 30, the opposite is 1, adjacent is 2, so the sine of 30 is 1/2. The cosine of 30 is adjacent over hypotenuse, or the square root of 3 over 2. Tangent is opposite over adjacent, and that's going to be 1 over the square root of 3, from which we would then have to rationalize, and we end up with the square root of 3 over 3. Now, once again, your sine and your cosine values are very important to know for these values. And remember, 60 degrees is pi over 3, and 30 degrees is pi over 6. We'll look at those very much in depth in the coming weeks. All right, and here are those values. All right, now this right here explains why what we just talked about is the case. And it's an identity. It is actually an identity of the trig functions, that the sine of theta and the cosine of 90 minus theta are going to be the same value. Now, what do we know about theta and 90 minus theta? Well, they're complements of each other. So the sine of one angle is equal to its complement, the cosine of its complement. I'll figure out a way to say that in just a second. The sine of an angle is equal to the cosine of that angle's complement. That's the best way to say it. All right, and here are all of the cofunction identities. It's true with all these. Guys, these are not something that I'm going to ask you to remember. They're not even something that we're really going to use very much. It's just a good property to know because of the way that they relate to one another. Now, if we wanted to find a cofunction with the same value, it's real easy. If we're talking about sine, remember, the cosine is its cofunction, and we want the cosine of the complement of that. Well, what angle is going to add to 72 to get 90? Well, that'd be 18 degrees. Cosecant, well, cosecant, so secant is its complement. Pi over 3 is going to add to pi over 6. Now, in case you're having some problems with that, remember we need a common denominator, so we've got pi over 3 plus pi over 6. I'm going to confirm that this equals pi over 2. So when we get common denominators, we're going to have 2 pi over 6, that's pi over 3, plus pi over 6 equals 3 pi over 6, which is equal to, of course, pi over 2. All right, now when we go to apply this to other things, one way that we can do that is an angle of elevation or an angle of depression from a certain point. And all that is the angle of depression means you're going to look down from horizontal to see something. Angle of elevation means you're going to look up from horizontal to see something. And all you're going to do is you're going to form the triangle out of that and use all those properties we've talked about and those relationships between the sides to be able to find, and angles, to actually find what a missing side is. Guys, when you do these, what you want to do is draw your triangle, label everything you know, and then look for, they'll always ask something that's going to tell you what you're looking for. Label what you're looking for with X or some variable. When you do that, then you're going to have at least one of the other sides. For instance, I might have this one, and they want to find how far above, how high that plane was. And they would probably give this value right here, how far up the guy was standing and all that. And you could get this triangle right here now, and they'd give you this angle of elevation. And what are we looking for? Well, if with respect to this angle, we have the opposite and the adjacent. What's going to relate the opposite and the adjacent? Well, that's going to use the tangent. So the tangent of theta we can use equals opposite x over adjacent 100. And then when we solve that, remember this angle would be given. We'd find that decimal and multiply both sides by 100 and all that stuff. And we'd end up finding what this x value was. Now, how do we find the total height of the jet plane? Well, we've got this part right here, and remember that is starting horizontal when where this guy's seeing, and then if we know what this height over here is, we would just add those two together. And it's not always going to be that complicated, but those are something that's really easy to do. So don't overcomplicate this stuff, guys. Draw the triangle, see what sides you have, and whichever side, an angle you might have, and then work from there to find what you need to know. All right, that's it. We'll do some work on this next time in class.